I'd like to welcome you to my presentation. My name is Uriah Daugaard and I'm a PhD student at the University of Zurich. The title of the presentation is Non-consumptive and Resource Availability Effects in a Ciliate Predator-Prey Pair. In general, a predator-prey pair is defined by the consumptive and non-consumptive effects of the predator on the prey, as well as the density effects of the prey on the predator, which we here call resource availability effects. Non-consumptive effects on the prey are, for instance, induced defensive strategies and stress-induced changes in behavior in the prey, which do affect the growth rate of the prey. Resource availability effects mean that, for instance, the search strategy and corresponding energy expenditure of the predator are functions of prey density. In fact, it has been shown that the conversion efficiency and the mortality rate of the predator are prey density dependent. However, at least the short-term interaction strength of a predator-prey pair is frequently assessed based only on the feeding rate of the predator, which mainly captures the consumptive effects of the predator. But non-consumptive effects and resource availability effects also influence the interaction strength because, as just stated, they affect prey growth rate, predator mortality rate, and predator conversion efficiency. To show the prevalence of non-consumptive effects and resource availability effects, the aim of our study was to show their presence in a widely used microbial predator-prey pair by focusing on a behavioral and morphological level. To do this, we carried out a short experiment with a ciliate predator-prey pair consisting of Paramecium caudatum as the prey and Didinium nasutum as the predator. In the experiment, we used 3 different culture combinations. In the prey monoculture, only the prey was present, with a density of 400 individuals per milliliter. In the predator monoculture, there were 60 predator individuals and nothing else. Finally, in the mixed culture, both the prey and the predator were present at the just mentioned abundances. Of each culture type, we had 4 replicates, meaning that we had 12 replicates in total. Each replicate consisted in 3 milliliters kept in a separate petri dish for 4 hours. After the 4 hours, we collected individual-based morphology, movement, and location data. For this, we recorded 3 videos of each replicate. Each video was 30 seconds long. The videos were then processed with the air package removing. On the left-hand side of the slide, you can see a frame of such a video with some individuals tracked. On this slide on the left, you can see the recorded trajectories of one replicate. In this figure, the predator trajectories are red and the prey trajectories are blue. This predator moves in helices, which can be seen in the recorded trajectories. On the side of resource availability effects, we analyzed the swimming speed, the displacement, and the body size of the predator. We hypothesized that in scarcity or absence of prey, the predator would swim faster and search in larger areas, and that it would decrease in body size due to starvation. Similarly, on the side of non-consumptive effects, we investigated the prey swimming speed and body size. In this case, the hypotheses were that the prey would either swim more slowly in the presence of the predator to avoid encountering it, or swim more quickly to evade it upon encounter. Of each recorded trajectory, we calculated one swimming speed value. For the predator, this was done by also taking into account that it moves in helices, that is, in a 3D movement type. In the figure on this slide, you can see the resulting distribution of the swimming speed of the predator. The green-colored histogram is for the predator in the mixed culture, and the orange one is for the predator in the monoculture. What can be clearly seen in this figure is that the distribution is distinctively bimodal. Based on this, we classified each predator individual as either slow or fast-moving, with a threshold at 1500 micrometers per second. To quantify differences between the 2 culture types, we fitted a skew-normal distribution to this data using maximum likelihood estimation. On this slide, we see the results of fitting the skew-normal distribution, in the top left figure for the slow predator and in the top right figure for the fast predator. The estimated mean swimming speeds are shown in the figure at the bottom of the slide. On average, predators swam faster in the monoculture than in the mixed culture. The slow predator swam about 7% faster and the fast predator swam 20% faster. Similarly, for the prey, we also calculated one swimming speed estimate per trajectory. The resulting swimming speed distribution is shown here as histograms, in red for the prey in mixed culture and in blue for the prey in monoculture. Again, you can see that the distribution is bimodal, although less distinctively so. To the distribution, we fitted a weighted mixture of two normal distributions using maximal likelihood estimation. The estimated weights are shown in the figure on the bottom, and as you can see, there was a significant difference between the two culture types. In fact, the proportion of prey individuals showing the fast movement behavior increased by 12.5% from 65.3% in the monoculture to 77.8% in the mixed culture. To analyze predator displacements, we estimated its mean square displacement, MSD, for different time lags. The figure shows the log-transformed MSD as a function of the log-transformed time lag, both for the fast and the slow predator in mixed and monoculture. Overall, the predator made larger displacements in the absence of prey. For instance, in 1 second, the MSD of the slow predator was about 37% larger in monoculture than in mixed culture. Similarly, in the same time, the MSD of the fast predator was about 14% larger in the monoculture than in the mixed culture. The follow-up question to this is, does the movement of the predator also depend on the local prey density or only on its absence and presence? To answer this question, we calculated the local number of neighbors for each predator individual recorded in a subset of the data, given a certain distance threshold. For the same individuals, we also calculated their subsequent displacement in 1 second. The resulting data is shown on the left as a flipped ridge and rug plot. To this data we fitted a linear model with displacement as the response variable and the number of local prey neighbors as the explanatory variable, as can be seen in the bottom figure. We found that the predator made larger displacements the fewer prey neighbors it had. For each unit decrease in number of local prey neighbors, the slow predator increased its displacement by 3.7% and the fast predator by 2.3%. These patterns persisted in a distance threshold sensitivity analysis. Regarding the body size analysis, and to keep it short, in an analysis similar to the one done for the swimming speed, we found that the fast predator was about 15% smaller in the absence of prey. We found no significant change in body size in the slow predator and in the prey. The figure on this slide shows the relation between species body size and its swimming speed. The left panel shows the slow predator, the middle one the fast predator, and the one on the right shows the prey, all both in monoculture and in mixed culture. Swimming speed increased with body size in the slow predator and the prey, but this was not the case for the fast predator. To conclude, we have seen that the species were able to react to changes in the abundance of their trophic component. On the side of non-consumptive effects, we found that proportionally more prey individuals swam faster in the presence of predators. This could be an attempt at increasing their evasion rate when they encounter a predator. Regarding the resource availability effects, the predator swam faster and covered larger areas in the absence of or scarcity of prey, likely in an attempt of increasing the encounter rate with the prey. Thus, we have confirmed the presence of both non-consumptive and resource availability effects in a commonly studied predator-prey pair. Yet, if predator interaction strength is assessed only with predator consumptive effects, the non-consumptive effects might partially be captured, while resource availability effects of prey on predator mortality and conversion efficiency are ignored. The estimation of predator-prey interaction strength should therefore account for consumptive, non-consumptive, and resource availability effects. Further, there is strong evidence of non-consumptive effects affecting community stability, but it remains to be determined what the role of resource availability effects is in this regard, and thus also how strong the joint impact of consumptive, non-consumptive, and resource availability effects is on community and ecosystem stability. I'd like to thank my two co-authors, Professor Fuhrer and Professor Paci, as well as the Predictive Ecology Group at the University of Zurich. If you have any questions or comments, please do get in touch with me. You can see my contact details in the bottom right corner. Thank you for listening to my talk, and I hope you enjoy the remainder of the ESA conference.